Hello, everyone, and welcome to Lecture 12 of Computer Architecture. Today we're going to talk about floating point instructions. Last time, we looked at memory addressing, specifically how to address memory or how to represent addressees in control flow instructions like branches and jumps. And we also looked at how to access small data from memory, like loading bytes and storing bytes. We started by talking about branch addressing, and we said that branch instructions use the I format, and the I format only gives us 16 bits to represent the label, but the label points to an address that is 32 bits long. So what we did in order to represent a 32-bit address using just 16 bits is we used PC relative addressing, where instead of representing the full address, we represented the address, the label, as an offset from the address of the branch instruction itself. So the target address was going to be the program counter of the branch instruction plus 4 plus the offset that is stored in these 16 bits times 4. And the reason we did times 4 is because we know that the offset is always going to be a multiple of 4. So we don't need to store 2 bits, the 2 0 bits. Instead, we store the value divided by 4, and that gives us additional bits to represent the offset. An example of how we can take a branch instruction and represent the label here as an offset, and we did that by applying this rule for branch addressing, where the target address is PC plus 4 plus the offset times 4. We then instructions. We said that for jump instructions, we have a third format called the J format. That's just an opcode, which is 6 bits, and then the address, the address to represent the label, which is 26 bits. But again, addresses are 32 bits, and we only have 26 bits, so we need some way to represent a 32-bit address using just 26 bits. And to do that, we did what it was called pseudo-direct jump addressing, where again we observed that the instructions are always a multiple. Instruction addresses are always a multiple of 4, so we don't need those 2 bits. So that gives us 28 bits, and then the remaining 4 bits we get from the upper 4 bits of the program counter, and this is based on the observation that in most cases the address we're jumping to is going to have the same upper 4 bits as the address of the instruction, because programs are usually not large enough such that different instructions might have a different value of the top 4 addresses. Nevertheless, we saw how we can branch and jump to farther places than what can be represented. Also, we did an example also of how we use this technique to represent a label in a jump instruction. And then we saw how we can branch far away by converting a branch to a label into a jump to that label and a branch over the jump instruction. And we saw how we can convert a jump to a far label into a jump register instruction, and we just put the label we want to jump to in the register. And this also led us to the discussion of how we can store 32-bit constants in registers, because we know that immediate instructions only create 16-bit constants. So if we want to create a 32-bit constant, we can do that by combining the load upper immediate, which initializes the top 16 bits of register, and then combine that with or immediate, which will initialize the lower 16 bits of the register. Finally, at byte and half word operations, we said that so far we've been talking about words where the data that we've been loading and storing has all been 4 bytes. So we went on to talk about the load byte and the load half word and the store byte and the store half word instructions, which allow us to load just 1 byte or just 2 bytes from memory. And we said that these are useful when we are processing character data. So for example, in ASCII, every character is 4 bytes, or Unicode, where in Unicode every character is in ASCII every character is 1 byte, and in Unicode every character is 2 bytes. And then finally, we did an example of how we can, if these X's were arrays of characters, we did an example of how we can convert this code into MIPS code by using load byte and signed, and load byte and store byte. Okay, so this was an overview of what we covered last time. Any questions? Okay, if there are, then let's move on to today's topic, which is floating point instructions. First of all, before I talk about floating point instructions, let me talk about the floating point coprocessor. So the way that floating point operations happen in the CPU is in addition to having our ALU for integers and our whole processor that processes integers and addresses, we also have what we call a coprocessor, which does the floating point instructions. And this coprocessor comes with an extension of the MIPS ISA that works on floating point instructions. Hypothetically, you can imagine that you could have a MIPS processor without floating point instructions, even though in practice that's not common to have. However, but we think of the floating point hardware as a coprocessor, and this coprocessor comes with extensions to the MIPS ISA for performing floating point operations. And also, the coprocessor comes with separate floating point registers. So the 32 registers that we've talked about so far are A registers and our S registers, our T registers, return address, all these registers. We are actually not going to use these when we process floating point operations. We're going to have a separate set of registers. So we have a separate set of 32 registers that are 32 bits each. So 32 single precision registers. And we're going to use these registers for floating point instructions. And the human readable names for these registers are just F0, F1, up until F31. Okay, so whenever we have a floating point instruction, and that instruction is going to have fields, the register fields are actually going to refer to these floating point registers as opposed to referring to the registers that we saw before. Now, each of these registers are 32 bits because these are 32 single precision registers. However, as you know, with floating point, we might be processing single precision, or we might be processing values that are in double precision. And double precision values are 64 bits. So what we're going to do with double precision is we're going to pair up these registers whenever we use double precision. So whenever we use double precision, F0 and F1, so register F0 and register F1, which are each 32 bits, together they're going to behave as one 64-bit register. Registers F2 and F3 together will behave as one 64-bit register, etc. Okay, so whenever we have double precision, rather than having 32 single precision registers, we're going to logically have 16 64-bit registers. And the way we address these registers is by using the even numbered register in the pair. So for example, if we're processing with double precision, then when we refer to F0, this will access the 64-bit word that is stored in F0 and F1. If you want to address F2, F3, we use F2 to address them. Okay, so this is how we represent double precision and single precision registers. And like the floating point instructions are going to operate on floating point registers. So a floating point add instruction, it's going to take, we'll see that later, but it's going to take 3 register operands, just like an integer add operation took 3 register operands. However, these register operands, they're also going to be 5 bits each, but these 5 bits will be interpreted as a floating point register rather than being interpreted as a integer register. The intuition behind why we do this is that programs don't really process integer and floating point data together, right? So usually you don't. If you have an integer, you use integer instructions on that. If you have a floating point value, you use floating point instructions on that. You don't use floating point instructions on integer values. You don't use integer instructions on floating point values because that doesn't make sense. Because then the integer will interpret the floating point value as if it was an integer, but that's not how the 32 bits are supposed to be interpreted. Okay, let's take a look at these registers and the conventions with these registers. So F0 to F3 in our registers are going to be the return values of the function. F4 to F11 and F16 to F19 are used for temporary values. F12 to F15 are used for arguments. And then finally, F20 to F31 are used for saved registers. So this is the convention for using the floating point registers, just like we had a convention for using integer registers. Notice how here we don't have things like return address, stack pointer, frame pointer, and the reason is that all of those are part of the all of the addresses are integer or behave like integers. They're not floating point values. So we're not going to ever, we use the same add instruction to operate on integers and addresses, but we're not going to use floating point addition, for example, to operate on an address value, right? Because that's not how addresses are supposed to be interpreted. Okay. So given kind of this introduction, let's take a look at what different instructions are available with the floating point cooperator. So the floating point instructions in MIPS are as follows. We have single precision arithmetic. So add.s means do a single precision add. Sub.s is a single precision subtraction. Mul.s is a single precision multiplication. Div.s is a single precision division. So for example, we can do add.s, f0, f1, f6, and what this means is that f0 is equal to f1 plus f6, where f0, f1, and f6 are all single precision values. Okay. We can also do double precision arithmetic, and as you probably guessed, they're very similar to these single precision values, but rather than having .s, we have .d. So add.d will do double precision addition, sub.d will do double precision subtraction, etc. And as an example, we can do something like mul.d, f4, f4, f6, and what this means is that f4 is equal to f4 times f6, where f4 and f6 are double precision, are registers that hold double precision values. And remember that here F4 refers to both F4 and F5, right? Because F4 as a single precision register is 32 bits. So this actually refers to F4 and F5 in single precision. So the F4 register for double precision is the same as the F4 and the F5 registers for single precision. And that's why you'll notice that these instructions are even numbers, they're not odd numbers. Okay, we will never have an odd number when we use double precision instructions. We also have load and store instructions, and these look like this. We have LWC. This is load word in coprocessor 1. So this is a load instruction that will load a single precision value. Because remember, a word is 32 bits, and a single precision, a floating point value in single precision is also 32 bits. We have LDC1. This does load double in coprocessor 1. So this will load a double value. And we have store word C1, so store word in coprocessor 1, this will store a single precision value. And we have store double in coprocessor 1, SDC1, this will store a double precision value. So for example, if we wanted to load a double precision value from memory, we would do this, LDC1 and then F8 and then 32 SP. And what you'll notice here is that even though this is a floating point instruction, the base register for this instruction is going to refer to not a floating point register, but a register in the main processor. Okay, so whenever we have load and store instructions, the source register is going to be interpreted as a register in the main processor because that's where addresses are stored. However, whenever we have the other registers, so the source or the destination register, if we're doing load or store, that's going to be interpreted as a floating point register. Okay, so the base registers are integer registers, not floating point registers. Any questions so far? Okay, so someone is asking if we want to add an integer and a float, we do floating point instructions and consider integer as a float. So if we want to add an integer and a floating point number, the hardware does not do that. Okay, so at a high level, when you write code, and this code adds an integer and a floating point number, what actually happens is that the compiler takes that and converts it into code that converts the integer to a floating point number and then does a floating point addition. Okay, so the hardware does not deal with adding integers and floats, right? In the hardware, every instruction does a single operation. So adding an integer to a float is two operations. You first convert the integer to a float and then add two floats. What the compiler will do is that it will break that down and do the conversion and then do a floating point addition. Okay. So that's what I mean by that's what I mean by that you can't add integers using floating point instructions. How do you convert an integer into a float? I mean, it depends. Either you'll do that in software or you'll do that in hardware. So it depends if the hardware provides you with support for doing integer to floating point conversion. Some hardware does. I think MIPS does, but I don't remember right off the bat. Okay, so these are, we have arithmetic instructions, we have load and store instructions. We also have single precision comparison and double precision comparison. And the way we do comparison is as follows. We have C, so C for compare, dot, and then the type of comparison that we want to do, and then dot S. This will do single precision comparison, and C dot the comparison dot D will do double precision comparison. And these XX can be equal, less than or equal, etc. Okay. So here, for example, C dot LT dot S is do a single precision less than. And you'll notice here, before when we did less than an integer, we had set on less than. And what set on less than did is that it would set an integer register to 1 if some some value was less than another value. But the difference here with floating point registers is the following. So here when you do C.LT.S, what this is doing is like set on less than if F3 and F4. But the question is, what are we setting here? Okay, what are we setting? And it's the same thing for equal. So if F3 is equal to F4, we're going to set something. But whatever we're setting is not going to be a register. There's actually an implicit flag, and we call it the condition flag, in the MIPS, in the floating point coprocessor, that will get set whenever we have a condition value like this. Okay, so here if we do compare less than single precision F3 and F4, so F3 is less than F4, there's a bit in the coprocessor that will be set to 1. Otherwise, that bit will be set to 0. Okay, and how do we use this? Well, we use this in the branch instructions. So the branch instructions in the floating point coprocessor look like this. We have two branch instructions. We have BC1T and BC1F. So BC1T is branch if true, and BC1F is branch if false. And for example, if we do BC1T some label, then what this does, it will branch if true to this label. If what is true? If this condition bit is true. Okay. So if we want to do something like branch on equal, branch of less than, branch of greater than, we do a comparison. The comparison sets some bit in the coprocessor to 1 or 0, and then the branch instruction will read that condition bit and will branch the target label accordingly. Okay, so there's an implicit value that we are setting when we do a comparison, and there's an implicit value that we are reading when we do a branch. Any questions about this? We'll do an example shortly, but does anyone have any questions? Someone's asking, how do we reset the bit? Well, you don't really need to reset the bit, right? Because whenever you want to branch, you need to have done some kind of condition before you branch, correct? So why would you ever want to reset the bit? Okay, one final thing about instructions before we do an example. We do not have immediate instructions. Okay, so if you remember with add and subtract, with integers, we had this add immediate, and immediate, or immediate, etc. Well, with floating point, we don't have immediate instructions. Why? Simply with integer instructions, I can take a 16-bit value and then extrapolate that into a 32-bit value. okay? Because integers are just integers, right? They're just a sequence of zeros and ones, and we saw what integers mean. It means, you know, this bit times 2 to the power 0 plus this bit times 2 to the power 1. So a 16-bit value can be extrapolated into a 32-bit value simply by doing sign extension, okay, where you just add zeros to the left or add ones to the left. However, with a floating point, as you guys remember, the floating point representation is quite complex. The way we represent these 32 bits, there's a sign, there's an exponent, there's a fraction, etc. So doing something like an add immediate with floating point doesn't really work, because you can't take a 32-bit floating point and represent it as a 16-bit value. Okay, you can't just do sign extension, right? Because you have different fields, and each field means something different. What we do in order to, rather than representing immediate, rather than having immediate instructions, whenever we want to add to some constant or want to multiply by some constant, what the compiler will do is it'll find all the floating point constants in our program and it'll put them somewhere in global memory. And then every time we need to use a constant in our floating point code, what we will do is we will load that constant from global memory. And as we saw before, the way we access things in global memory is using the GP register, the global pointer register, where we put all our constants. Okay. So with that, let's do an example. So let's say we wanted to write a function like this, floating point to Celsius, that takes a floating point, that takes a Fahrenheit, sorry, not floating point Celsius, Fahrenheit to Celsius, that takes a Fahrenheit value of temperature and converts it to a Celsius value. Okay. Now, how do we convert from Fahrenheit to Celsius? Well, we do that by subtracting 32 and then multiplying by 5/9. Okay. So let's do that. First of all, Fahrenheit, the argument is going to be placed in F12. F12 is the register where we put the arguments in. Remember, it's F12, F13, F14, F15. And then the return value is going to be stored in F0. Okay. And then if you remember, we also have some registers that we use for temporaries. So we'll see those registers shortly. Okay. And then also something else we need to do here is that all the constants in my code need to go somewhere in my global memory. Okay, so 5.0 has to be put somewhere so that when I use it, when I want to use it, I can load it. 9.0 has to be put somewhere, and 32.0 has to be put somewhere. So where do we put them? Well, for now, what we will do is we will put 5.0, 9.0, 32.0, and 36, 40, and 44 respectively. These are the offsets from the in global memory. So 5.0 is going to be at the global pointer plus 36. Okay. All right, let's convert the code now. So what's the first thing that we want to do here? So I want to compute 5.0 over 9.0 times Fahrenheit minus 32.0. So what's the first operation that I need to do? Okay, so actually the evaluation in C happens from left to right. So I'm going to do the division first. But before I do the division, what do I need to do? Right, I need to get 5.0 and 9.0 from memory. Okay, and then I can divide them. All right, how do I, so what do I get first? Like I'm gonna get 5.0 first. How do I get 5.0 from memory? Where is 5.0 in memory? It's at offset 36 from the global pointer register, right? So I want to load it from there. What instruction do I use to load? I'm going to use LWC1, right? Load word coprocessor 1. So I'm going to do the arithmetic instructions take the .s and then .d suffixes. So the load and store instructions will use load word and load double to distinguish themselves. Okay, so I'm going to use LWC1 and then I'm going to load that word at 36 an offset of 36 from the global pointer, and I'm going to put that in a temporary register. It's going to look like this. I'm going to do LWC1. Of course, I have a label for F2C because it's a function, and whoever calls it needs a label to jump to. And then I'm going to have LWC1. F16 is going to be a temporary register where I'm going to put the value that I loaded. And then 36 GP means that I'm going to load at an offset of 36 from the global point. Okay? All right, so now what do I do? I've loaded 5.0. What do I need to do next? Right, I need to load 9.0. Where is 9.0? Right, exactly. So I'm going to load 9.0 from 40 GP, and I'm going to put that in another temporary register, which is F17. So I'm going to do load word C2, C1, sorry, this is a mistake. It should be a 1 over here. So I'm going to do load word C1, F17, 40 GP. Okay? Clear so far? Any questions? Okay, so what do I do now? Right, I need to divide. What do I divide? Right, I'm going to divide F16 and F17, and then I'm going to put their result in F16 again. Okay, so I'm going to do div.s. This does a single precision divide, and then I'm going to put the result in F16 because I no longer need F16 to store 5 anymore. Okay, all right, so I've done my division. What's the next step? Right, so I need to do Fahrenheit minus 32.0, so I need to get 32.0 first. So that's correct. I need to do LWC1 to F17 from 44 GP. So 32 is stored at 32.0 is stored at GP plus 44. So I load from that location and I put it in a temporary register. And then I do subtraction. Subtraction, I know that Fahrenheit is in F12 and 32.0 is F17. So I'm going to do F12 minus F17. Where will I put the result of that? So I can't put the result in F12 because I might need F12 later on, right? So I'm actually going to put the result in F17 because I no longer need 32.0. So I'm going to do F12 minus F17, put the result in F17. So now 5 over 9 is in F16, and then Fahrenheit minus 32 is in F17. So what do I do next? Right, so I want to multiply F16 and F17, and since I'm going to return the result, I'm going to put the result in F0. Okay, so I'm going to do mul.s F0, F16, F17. What this means is that F0 is equal to F16 minus F17. Okay, and then finally, once I'm done, what do? I put the value in the in F0. What do I finally do? I need to return, right? This is a function, so I need to return. So how do I return? It's not a trick question, guys. How do we return once we're done? Right, exactly. We just do jump register RA. Okay, so we can use the floating point and the integer instructions interchangeably. Okay, so all the control flow, the jumps and stuff are just all the control flow is gonna happen through the integer instructions, and you'll see. I'll show you another example where we will do this more. Okay, but yes, we just simply do jump register and we return. Okay. Any questions? Is this clear to everyone? Okay, well, since this example is clear, let's do more of an elaborate example, and we're actually going to use this example to review not just floating point instructions, but several things that we've done. So this is probably the biggest example that we've done so far in terms of MIPS programming. So let's say I wanted to multiply two matrices. You guys have taken Math 218, so you know how to multiply matrices. If I want to multiply two matrices and then add, so I want to x is equal to x plus y times z, where each of these, x, y, and z, are 32 by 32 matrices, and the values are 64-bit double precision elements. Okay, so how do I do matrix multiplication? Well, this is the code that does it. Okay, I didn't put this in a function just so that we don't have to worry about setting up the stack and everything. So I'm gonna have three nested loops: I from 0 to 32, j from 0 to 32, k from 0 to 32. Okay, and then we're gonna do x of ij is equal to x of ij plus y of ik times z of kj. Okay, so this code does matrix multiplication. I'm not going to go into why this code is for matrix multiplication. You can kind of cover that on your own. But what we care about in this course is, given I have this code over here, how do I take this code and generate the corresponding MIPS instructions that execute it? Okay. So first, we're going to put our loop indices in S0, S1, and S2. These are integers, so we're going to put them in S0, S1, and S2. And we're going to put our array base addresses in S3, S4, and S5. So X, Y, and Z are arrays of double. We're going to put them in, but we're going to put them in S3, S4, and S5. And notice an important point here: X, Y, and Z are not doubles. They are arrays of doubles, which means that X, Y, and Z are pointers. They're memory addresses. They're 32-bit. They're treated as 32-bit integers. And that's why we have them in S3, S4, and S5, not in the F registers. Okay? So again, each of these arrays are going to have 32 by 32 doubles. And so each one of them is going to be 8 bytes. Okay, questions about this code before we go on to generate the MIPS code? I hope it's clear to everyone.
Sir, you mean the
Yes,
base address of X, Y, and Z are in S3, S4, right?
yes, the base address. So the array base
Oh,
addresses are in X, Y, and Z.
okay, thanks.
Yeah, you're welcome. Okay, so let's go on and generate code for this loop over here. And I put it up here as a reminder. I also put up the these where each local variable is as a reminder. So what do we do first? Okay, we're gonna have labels for each loops, of course. Once I generate the condition for the loop, I will label it, right? So I don't label I equals 0, right? I'm gonna label the comparison, because when I come back to the loop, I don't want to repeat I equals 0. I just want to repeat the comparison. Okay, so the label doesn't come just yet. I need to do something before the label. What is it? What's the first thing I do in this code? No, I don't load anything. What's the first thing that this code does? Right, set I to 0, exactly. So how do I set I to 0? I do add immediate S0, 0, 0. Okay, so I initialize I to 0. Remember, I is in S0, so I want to set S0 to 0, and I do that by adding 0 and 0. Okay? All right, so I set I to 0. What do I do next? I need to compare I to 32. How do I compare I to 32? Notice I'm intentionally not doing I less than 32. I'm doing I not equal to 32. Okay. So, because we were trying to kind of show several concepts in this example. So we haven't done this before, actually, right? We haven't done equality comparison with a constant value. We've done equality comparison between two different registers, or we've done less than between two registers, or less than between a register and a constant. But we haven't done equality comparison with a constant. Do we have a branch if equal immediate? We don't have something like that. So how are we going to compare I to 32?
Sir, we store 32 in a register and we compare it a branch equal or a branch not equal.
Right, excellent. So that is exactly what we're going to do. Okay, so what we will do is we will put 32 in a register and then we'll use the branch instruction to compare two registers. So since I'm using 32 in multiple places, I'm going to apply an optimization while I'm generating this code. And I'm going to put 32 in a register at the very beginning, and then I'm going to use it multiple times later on, okay? So I'm going to do add immediate T0032. So now the register T0 has the value 32 inside of it, and we're going to use it several times throughout the code. Okay. Okay, so now that I have I is in S0 and 32 is in T0, what do I do? I'm going to do branch if equal, exactly. So if they're not equal, I'm going to continue into the branch. If they are equal, into the loop. If they are equal, I'm going to exit the loop. So I'm going to do branch if equal S0 to T0 to, I'm going to call this L0 end. L0 end is going to be loop zero's end. Okay, so if I is equal to 32, we're going to exit the loop. Okay, otherwise we're going to continue the loop. And notice that I labeled the equality comparison here L0 because when we're gonna jump back to the beginning of the loop, we're not gonna jump back to I equals 0. We're gonna jump to I not equal 32. Okay. Okay, so if they're not equal, if they're equal, I'm gonna branch. If they're not equal, I'm gonna continue. So if I continue, what's the next thing I need to do? Right, I need to set j to 0. Okay, so this is another thing that we're trying to show you with this example. So we are showing you how to handle nested loops, and really it's not that complicated. All you have to do is just apply the same thing that you did for one loop, but apply it multiple times. So the next thing is to set j to 0. So we're going to use the same technique we did here. We're going to do add immediate s1 0 0. So that will do j equals 0. And now we want to check if j is 32. If j is not equal to 32, we're going to go in. If j is equal to 32, we're going to exit the loop. So what do? Well, same thing we did here. We're going to do if S1 is equal to 32, where is 32? 32 is in T0. So if S1 is equal to T0, we're going to exit the loop. We're going to go to L1 end. Otherwise, we're going to continue into the loop. And notice how I labeled this L1, because when I want to jump back to the beginning of the condition of this loop, I'm going to go to the comparison, not to the initialization of j to 0. Okay. All right. So if the condition is true and I continue in here, what do? Right, I'm going to set k to 0, so same thing. I'm going to do add immediate. Now k is in S2, so we're going to add immediate S2 equals 0 plus 0. Okay, and now what do? Again, I'm comparing k to 32. So if S2 is equal to T0, I'm going to exit. If S2 is equal to 32, I'm going to exit. Otherwise, I'm going to continue into the loop. Okay, so if S2 is equal to 0, I'm going to go to the end of loop 2. Otherwise, I'm going to continue to the next instruction. Okay, so now that let's say I enter this loop, enter the third loop. Now I want to do x of ij is equal to x of ij plus y of ij times y of ik times z of kj. So I'm going to skip this for now. Okay, I'm going to show you in the next slide how we're going to generate code for this long instruction. But assume that now we generated code for this. Okay, now after we're done with this, what do? Okay, after I'm done executing the body of the innermost loop, what's the next step? Okay, one at a time, increment kij is a lot. So what's the first next step? Increment k, exactly. So the first thing I do is I increment k. How do I do that? Right, add immediate. Where's k? K is in S2, so I'm going to do add immediate S2, S2, 1. After I increment k, where do I go? What do? No, not L2 end, right? How does a for loop work? You do the comparison, you execute the body, you increment the value, and then where do you go? You do the increment, and you go back to the condition again. So where is the condition for k not equal to 32? Right, it's in L2, exactly. So we're going to do jump L2. Okay, so now we're going to keep around. You're going to get looping until finally, what happens? The condition becomes false. Once the condition becomes false, where am I going to go? I'm going to go to L2 end. Okay, so L2 end is going to be my next instruction over here. And what do I do at L2 end? What happens when this whole loop is over? What's the next thing that I need to do? Right, I need to increment j. So when I exit this loop, when I exit the third loop, I'm going to go back up here and I'm going to increment j. So when I exit, I go to L2 end, and at L2 end, I'm going to increment j. So I'm going to do j equals j plus 1, add immediate S1, S11. Okay, and then I'm going to do the same thing. Okay, so I'm going to, once I increment j, where do I go? I go to the condition for the second loop, which is L1. So I'm going to do jump L1, and then I'm going to keep looping in L1 until this becomes false. And when I get to L1 end, I'm going to increment I. So I will do add immediate S0, S01. And then once I increment I will go back to the condition for the zero loop. So I will do jump L0, and I will keep going until the condition becomes false. Once the condition becomes false, I will do L0 end, and then here L0 end will be just whatever code comes after these three loops. Okay. So I've shown you how to generate code for these three nested loops. Now we want to go into the body of the loop. Before I show you how to generate code for the body of the loop, any questions? Everything's clear? Okay. All right, so what we want to do now is we want to generate code for the body of the loop here. But one interesting thing to note is that, what's the first thing I need to do here, by the way? What's the first thing I need to do? I need to load y and z, exactly. So how do I load y of I, k? So remember, the load instruction takes what? It takes a base register and then offset. Okay, however, I have several problems here. I don't have constant offset. That's one, the first problem. And the second problem is, not only do I not have a constant offset, I actually have two offsets. Okay, I have two non-constant offsets. So what do I do? Well, what I need to do is I'm going to have to calculate the address of x of ij, and then I'm going to just have to load from that address with offset 0. Okay, so the question now is, or same thing for y and same thing for z. So the question now is, how do I calculate the address for a two-dimensional array access like this? Okay, so someone's saying, can't we do I of k of S0? No, we can't, right? Because the load instruction uses the I format. The I format takes a 16-bit constant. It doesn't take two other registers. Okay. So how do I find the address for y of I of k? Let's take a look a little bit about how the memory is laid out. Okay. So how do I calculate the address of x of I j? Okay. So someone has given an answer for y of I k. That's close. It's not 100% true, but it's very close to the answer that you gave. So let's take a look at why. So an array in memory is laid out like this. If I have two-dimensional array, okay, what's going to happen is that the first row of this array will be put in memory. So this is a 32 by 32 array. Okay, I know that it's actually 8 by 8 in the picture, but just imagine that this is a 32 by 32 array. And let's say I want to access the element ij. So I would point to the row and j points to the column. So let's say I want to access this element over here. Okay, how do I do that? Well, the way that two-dimensional arrays work is that we're going to have the first row of the array. So this corresponds to when I is 0, and followed by the second row of the array, followed by the third row of the array, etc. Okay, so what is the index of this element in x of ij? Well, it's going to be I times the number of elements in each row. Okay, so that's going to be 32 plus the index j. Okay, so the index of this element is going to be I times 32 plus j. Okay, in other words, what this means is that if I treat this 2D array as a 1D array, then the index into that 1D array is going to be I times 32 plus j. Is this clear? Any questions about this?
Sir, why 32? And isn't it a word of four?
No, the 32 over here is the number of elements in the row. Okay, so every row is 32 elements. Okay, so if I is 3, okay, 0, 1, 2, 3. If I is 3, then the number of elements in these 3 rows is going to be 3 times 32, and then I'm going to add j. Okay? So the
Okay,
32
thanks.
is coming from the fact that the number of elements is 32 in the row. Okay, now that I have the index, what I want to do now is I want to calculate the actual address. Okay, so I know that the first element is located at the value in x. So x is the address of the array. So x will point to the first element. So how do I get the address of the element at index I times 32 plus j? What do I do? Can I do x plus I times 32 plus j? I can't. The answer is I can't. And why is that? Well, yeah, right, we should compute it, but how do we compute it? We need to multiply it by not 4 because this is double precision. So each one of the elements in the array is a double, and the double are 8 bytes. But you're correct that we need to multiply it by the size of the element. So the address of x of ij is going to be, recall that each element is 8 bytes. So the address is going to be x plus I times 32 plus j times 8. Okay? So what I'm going to need to do is I'm going to have to calculate this address, and then I'm going to load from the value that I get. So let's go back and see how to do that. So the first thing I'm going to do is the multiplication comes before the addition. So first thing I want to do is I want to load the operands of the multiplication. So I'm going to start by loading y of ik. How do I load y of ik? Well, I need to do y plus I times 32 plus k times 8. Okay, so the first thing I'm going to do is I'm going to take I'm going to multiply it by 32. How do I multiply by 32? Is there a cheaper way of multiplying by 32? I can do mul, so I is in S0. I can do mul S0 32. That's one way to do it. Is there a cheaper way of doing it? Now, this is a complex example. I'm throwing a lot of things at you at the same time. Yes, we can shift. So our first thing we're going to do is we're going to do I times 32, and we're going to do that by shifting by 5, because 32 is 2 to the power 5. So rather than multiplying by 32, we're just going to shift by 5. So I'm going to do shift left logical, T1 S0 5. Okay, so that's I times 32, and then I want to add k. So where is k? K is in S2. So I'm going to do add T1 S2. So T1 now is T1 plus T1 now has I times 32 plus k. Now I want to multiply all of this by 8, right? Because we're looking for, because every element is 8 bytes. So how do I multiply by 8? Again, I can shift. So I'm going to do shift left logical T1 3. So I'm going to shift T1 by 3. That's now T1 has I times 32 plus k times 8. Okay, and now what do I do? Now I need to add y. Okay, so where is y? Y is in S4. So now I'm going to do T1 is equal to S4 plus T1. So now T1 is going to be y plus I times 32 plus k times 8. So someone's asking why we didn't use multiplication here. Well, whenever you multiply by a power of 2, that's like shifting. Okay, so a cheaper way of multiplying by a power of 2 is just shifting by a value. Okay, so multiplying by 32 is like shifting by 5. Okay, and it's much cheaper to shift than to multiply. You guys remember when we looked at the multiplier, we saw how expensive it is. So we'd rather shift if we can. Okay, so now in T1, we have the address of y of ik. Now what do we do? Now that I have the address of y of ik, what do I do? I need to load it, correct? So what instruction do I use to load? Remember, this is a double. Not LW. LW is for single precision values. I'm going to use LDC1. I'm going to use LDC1, right? So I'm going to use here LDC1. So load double coprocessor 1 from 0 T1. Here I'm just going to treat T1, which is the entire address, as just a base register and with 0 offset. Okay, and I'm going to put the result in F18. Notice how this is an even number because I'm loading a double value. So this is going to use both F18 and F19. Okay, then I'm going to do the same thing for Z of kj. So just to kind of speed things up, I'm going to go through it quickly. I'm going to do k times 32, and then I'm going to add j, and I'm going to multiply that by 8, and then I'm going to add z, and then now I have the address of z of kj, and I'm going to also load that into F20. Okay, and now what do I do? So now I have y of ik in F18 and z of kj in F20. What do I do now? I'm going to multiply them. Do I use mul.s or mul.d? Mul.d, right, because this says double precision. So I'm going to do mul.d F18. So now F18 is equal to F18 times F20. So now I have this product in F18. Now what I need to do is I need to add x of ij. How do I add x of ij? Well, I need to load x of ij first. So let me do that. I'm going to first of all, I need to calculate the address. So I'll do I times 32 plus j times 8 and then plus x. Okay. Now that I have the address of x of ij, I can load it. So I'm going to load it into F16. Okay. And then I'm going to do F16 plus F18 because the product is in F18. So I'll do F16 plus F18. Okay, so I'm going to do add.d. So now I have F16 is equal to F16 plus F18. So now the whole value is in F16. And now what do? I'm going to store it back in x of ij. So I already have the address of x of ij. It's in T1. So what I'm going to do is I'm going to store double coprocessor 1 the value F16 at 0 of T1. By the way, just a kind of a disclaimer here, I've done multiple optimizations as I'm generating this code. Things like reusing T1 for here and here by detecting that these are the same. Also, I did some reordering by loading these two and multiplying them before loading this value. So usually a compiler will not do these optimizations on the fly. It will generate unoptimized code and then it will optimize it later on. So here, as I'm generating code, I skipped a few steps and I kind of optimized some things on the fly. But just kind of want you to be aware that compiler will not do exactly this. However, if you want to understand why, of course, you can take the compiler class and we go into why we don't do that. But for this course, I think it's okay. If it's okay to kind of do these optimizations on the fly unless we ask you not to do them. Okay, so this is the code that gets generated for this expression over here. Okay, any questions? All right, if there are no questions about what we covered today in section 3.5, and that is all for today, and I will see you next time. Bye, everyone.